Okay, let's unpack this. Think about all the metal objects around you right now.
Yeah, everywhere.
Your phone case, maybe your coffee mug, the structure of the building you're in.
Yeah.
Metals are just fundamental to our world, right? But they face this constant, relentless enemy, corrosion.
Rust, degradation, yeah. It's always working against them.
That slow decay of materials, it never stops. But what if you could give those metals a kind of invisible suit of armor? That's what we're diving into today. Metal passivation. It's a process that essentially transforms the surface of a metal to protect what's underneath.
Right.
We've gone through a stack of material on this topic, and we're going to try to extract the absolute core knowledge and insights for you.
And our goal in this deep dive is, well, pretty straightforward. We want to understand what passivation is, how it actually works at a fundamental level, why it's so critically important in countless industries, explore the different ways it can be achieved, and then maybe zoom in on a common practical example. We're aiming to cut through the sort of dense chemistry textbook stuff and get to what really matters.
Exactly. Get ready to appreciate the metals you rely on every day in a totally new light. Let's jump in.
Let's do it.
So let's start with the most basic question. When we talk about passivation, what are we actually doing to the metal?
Essentially, you're treating the metal surface with a chemical solution. It's a controlled process, mind you, not just randomly dunking it in something.
Control.
And the result of this chemical treatment is the formation of a very thin protective layer right on the surface of the metal.
Okay, a layer.
Yeah, and this layer is typically an oxide or maybe another compound that is much less reactive than the underlying base metal.
Less reactive, got it.
And the whole point, the mission of this layer is really to act as a barrier. It sits between the metal and the environment, preventing or, significantly slowing down that corrosive interaction that leads to rust or other forms of degradation.
Okay, so it's not like applying a coating on top of the metal, like paint. It's actually changing the surface itself to create this protective skin. How does that process unfold?
That's a great way to think about it, yeah. It's a surface conversion. The typical steps involve, first, the chemical treatment.
Right.
You immerse the metal part in a specific solution, often an acid or an oxidizing agent, carefully selected for that particular type of metal.
Okay, the immersion.
Then comes the fascinating part, the protective layer formation. The chemicals in the solution react directly with the atoms on the very surface of the metal.
A direct reaction.
Exactly. This reaction causes that thin, stable layer to form. It kind of grows out of the metal itself, in a way. And crucially, this new layer is chemically much more resistant to attack than the bulk metal beneath it.
Wow, okay.
And the final outcome is, of course, corrosion resistance. With that less reactive layer now in place, it blocks the corrosive agents in the environment, things like oxygen, moisture, from reaching the vulnerable metal underneath.
Like putting up an invisible wall.
Precisely. An invisible wall.
That makes perfect sense as a mechanism. So, stepping back a bit, why does this process matter so much to the world around us? What are the practical benefits we actually gain from giving metals this invisible shield?
Oh, the benefits are huge. They're why this is such a fundamental process in manufacturing, really. Firstly, and most obviously, you get dramatically increased corrosion resistance.
Right, less rust.
Exactly. Metals can survive far longer in harsh conditions. Think about outdoor structures or components exposed to chemicals.
Makes sense.
That increased resistance translates directly into enhanced durability. Components last longer, which reduces the need for replacement, lowers maintenance costs, and improves the reliability of whatever the metal is part of. It's a big deal for longevity.
Reliability too, yeah.
And surprisingly, perhaps, in some cases, the process can actually improve the metal's appearance. It can give it a clean, uniform look by removing tiny surface impurities.
Interesting. So aesthetics too sometimes. And we actually encounter passivated metals constantly, probably without even thinking about it. Where are some of the most common places we see this?
Stainless steel is perhaps the prime example. Passivation is absolutely critical for stainless steel.
Okay. Why is that?
Well, it helps remove tiny contaminants, often called free iron particles, that get left over from the manufacturing process.
Free iron?
Yeah. And these particles are problematic because they can act like tiny little batteries on the surface, initiating rust spots even on stainless steel. And maybe more importantly, passivation enhances the natural chromium oxide layer that gives stainless steel its famous corrosion resistance. It makes that layer better.
Gotcha. What else?
Aluminum is another metal that's very commonly passivated. The process forms a stable oxide layer that prevents further unwanted oxidation and corrosion, keeps it looking good and performing well.
Right.
Even metals like titanium, which are naturally quite passive already.
Yeah, I thought titanium was pretty tough on its own.
It is. But passivation can boost its already high resistance for use in particularly aggressive environments, like, say, certain medical implants or demanding industrial applications.
Okay, so it can enhance even the tough stuff.
Yeah.
Now, here's where it gets really interesting for me reading the sources. It's clear it's not a one-size-fits-all approach. Yeah. There are different ways to actually achieve this protective layer, right?
That's right. While the core goal is always creating that stable barrier film, the specific chemistry and the process itself can vary quite a bit. One major category is chemical passivation.
Okay.
This is where you typically dip the metal into a chemical bath. Pretty straightforward concept.
Like the acid baths you mentioned earlier.
Exactly. Nitric acid passivation is a very common chemical method, especially, again, for stainless steel. Its job is to specifically target and dissolve those surface-free iron particles we talked about.
Right. Get rid of those troublemakers.
While simultaneously promoting the formation of that essential chromium oxide layer, it does both jobs.
Efficient.
Then there's also citric acid passivation. This is often presented as a gentler, maybe more environmentally friendly alternative to nitric acid.
Citric acid, like from lemons? Well, sort of.
Well, it's derived from citrus fruits, yeah, but used in industrial concentrations. It's also effective for stainless steel and aluminum alloys, forming that protective layer without some of the hazards you get with strong nitric acid.
So a greener option sometimes.
It can be, yes. It might be slower or require different conditions, maybe higher temperatures, but it's a powerful option, especially with environmental regulations.
Okay. Any other chemical ones?
Yeah, another one mentioned is chromate conversion coating. This involves immersing the metal in a solution containing chromium compounds. It forms a very thin film that offers good corrosion resistance and can also improve paint adhesion if you need to paint the part later.
Chromate. Okay, so that's chemical. What else is there?
Then you have electrochemical passivation.
Electrochemical. So electricity is involved now.
Exactly. Anodizing is the classic example here, widely used for aluminum, but other metals too. This method uses an electric current passed through the metal while it's sitting in an electrolyte solution.
Right.
So instead of just a passive chemical dip, the electricity actively drives the formation of a thicker, often more durable oxide layer on the surface.
Thicker, more durable. Makes sense with the electricity.
Yeah, and anodizing can even change the surface's color or texture, which is why you see aluminum in all sorts of colors.
Ah, okay. That explains colored aluminum parts. Interesting.
And finally, something perhaps less obvious, but mentioned in the sources, is mechanical passivation. Things like polishing and buffing.
Wait, polishing? How is that passivation? Isn't that just making it shiny?
Well, it's not creating a new chemical layer in the same way as the others, you're right. But the research highlights its importance because by physically removing surface contaminants, oils, and microscopic imperfections through polishing, you create a much cleaner, smoother surface. And this helps the metal's natural passive layer, that inherent ability some metals have to protect themselves, form more uniformly and effectively.
Ah, so you're preparing the surface, clearing the way for the natural protection to work better.
Exactly. It prepares the surface to be more corrosion resistant. Even if it's not passivation in the strictest chemical sense, it's about removing things that hinder protection.
That makes sense. Clearing the way for nature, or the subsequent chemical process, to do its thing. Let's zoom in on a specific case study because the sources discuss this in some detail. Using nitric acid on SS316 stainless steel. SS316 is everywhere, right? Kitchens, marine hardware, medical equipment.
It's a perfect example. Very common alloy. Why nitric acid specifically for SS316? Well, SS316 contains a good amount of chromium, and nitric acid is particularly excellent at selectively oxidizing that chromium.
Okay.
This process specifically grows that stable, protective chromium oxide layer that gives SS316 its remarkable corrosion resistance, especially against chlorides like salt water.
So it targets the chromium.
Precisely. And here's a truly fascinating detail the sources point out about that chromium oxide layer on SS316. Under the right conditions, it's actually self-healing.
Self-healing? What? How?
If the layer gets microscopically damaged, scratched perhaps, the underlying chromium in the metal can react with oxygen from the environment, just the air or residual moisture, to reform that protective oxide layer. It can effectively repair the shield automatically on a tiny scale.
An automatic repair system built into your metal. That's incredible.
It is pretty amazing, isn't it? It's a key part of why stainless steel is so durable.
Okay, so how does the typical process unfold when you're actually passivating SS316 with nitric acid in a facility?
Well, the steps are fairly standard for surface treatment, but each one is critical for success.
Yeah.
First, rigorous cleaning.
Cleaning first, always.
Absolutely. The surface must be free of grease, oil, dirt, metal shavings, and especially those free iron particles we mentioned. Detergents or solvents are typically used for this initial step.
Makes sense. Then the acid.
Then comes the nitric acid treatment itself. The cleaned parts are immersed in the nitric acid solution. Now, the exact concentration of the acid and the temperature of the bath are key variable.
Okay, it's not just one recipe.
No, definitely not. They're carefully controlled based on the specific grade of stainless steel. Even within 316, there can be variations and the required level of passivation needed for the final application.
Right, depends on how tough you need it to be.
Exactly. After the acid treatment, thorough rinsing is essential. You absolutely have to get all the residual acid off the surface.
What is that? What happens if you don't?
Well, any acid left behind could cause staining, etching, or even continue to react in ways you don't want, potentially compromising the surface later. So multiple rinses with clean, often deionized water are standard.
Okay, thorough rinsing. Got it.
And finally, drying. Drying the parts completely helps prevent water spots or stains, which don't just look bad, but could potentially become localized points where corrosion might start later on. Air drying or oven drying might be used.
Clean, treat, rinse, dry. Seems logical.
It is, but the devil's in the details. There are several factors the research emphasizes as influencing the success of this specific process, SS316 with nitric, the nitric acid concentration, for example.
Yeah, you mentioned that varies.
Right. A higher concentration can speed things up, make the process faster, but it also increases the risk of damaging the metal itself through unwanted etching or pitting if it's not very carefully controlled. It's a balancing act.
Risk versus speed.
Exactly. Temperature matters too. Increasing the bath temperature can also accelerate the reaction, but again, too high might potentially affect the structure or the protective properties of the oxide layer you're trying to form.
So faster isn't always better?
Not necessarily. And the treatment time, how long the part stays in the acid, is obviously crucial. It needs to be long enough to allow the protective layer to form completely and effectively, but not so long that it causes unwanted surface changes or over-etching.
Finding that sweet spot.
Finding the sweet spot, exactly. And it's also vital to consider the practical aspects. The handling, safety is paramount.
Nitric acid sounds pretty nasty.
It is. It's corrosive and hazardous. So proper personal protective equipment, gloves, eye protection, maybe respiratory protection, depending on the setup, good ventilation. It's absolutely non-negotiable.
Safety first.
Always. There's also the environmental impact to consider. Handling and disposing of used nitric acid solutions requires careful procedures to neutralize it and minimize harm to the environment. Regulations are quite strict here.
Yeah, can't just pour it down the drain.
Definitely not. And, as we touched on earlier, while nitric acid is common and effective for SS316, those alternative methods like citric acid passivation are increasingly used.
Right, the greener option.
Yeah, offering a safer handling profile and often easier disposal, potentially achieving effective passivation too, depending on the specific application requirements. Sometimes it's chosen for those reasons, even if nitric might be slightly faster.
So, given all these different types, chemical, electrochemical, mechanical, and then the variations within them like nitric versus citric, plus factors like time and temperature, how do manufacturers or engineers actually decide which passivation method is the right one for a particular job?
That's the key question, isn't it? The research gives us the core considerations, the decision tree, if you will. The absolute starting point is always the metal type itself.
What kind of metal is it?
Exactly. What kind of metal or alloy are we dealing with? Stainless steel, aluminum, titanium, something else. That dictates the possible chemical reactions and therefore narrows down the suitable processes right away. You wouldn't use the same process on aluminum as on stainless steel, generally.
Makes sense. Different chemistry.
A totally different chemistry. Then you have to consider the desired properties. What does this metal part need to do in its final application? What level of corrosion resistance is required? Is it just general atmospheric exposure? Or is it going into, say, A harsh chemical processing environment, does it need a specific appearance? A certain color from anodizing, maybe. Will it be painted later, requiring good paint adhesion? All these functional requirements play a role.
Function drives the choice.
Absolutely. And finally, the environmental factors where the metal will actually be used are critical. Is it going into a marine environment with salt water, a sterile medical environment, a high-temperature application, a common household appliance? The end-use environment helps determine the necessary level of protection and thus the best, most cost-effective method to achieve it.
Metal type, desired properties, and where it's going to live.
Got it.
Those are the big three. Wow. We've really gone from understanding what this invisible shield even is to how it forms, why it's basically everywhere, the different ways it's done, and even got into the real nitty-gritty of protecting specific materials like that SS316 stainless steel example.
Yeah, and it's clear from all the material that passivation isn't just some minor finishing step in manufacturing. It's an absolutely fundamental technique. It's what allows metals to perform reliably, to last longer, and ultimately be safe for use in countless critical applications that, well, we all rely on every single day without even thinking about it.
So the next time you interact with something made of metal, maybe the cutlery you're using tonight, or a piece of medical equipment, or even just, the shiny facade of a modern building.
They take a moment.
Think about that intricate, unseen protective layer that's almost certainly on its surface.
Yeah.
It's likely undergone a process like passivation, silently doing its job day in and day out to keep that metal strong and functional for you.
And maybe that leaves you with this thought to ponder, kind of drawn from the depths of all this material we looked at. How much of the reliability, the sheer durability, and the very trust you implicitly place in the metal objects that underpin your daily life? How much of that is entirely dependent on this invisible, carefully engineered chemical shield? It really makes you look at the materials around you with a different kind of appreciation, doesn't it?